All right, hello, welcome to the Off by One security stream. So this week kind of flew by, and it got to yesterday, and I was like, oh no, I haven't talked to anybody about having a guest on, and kind of rushing together to see what I can come up with. And I remembered the very first stream that I did was the browser exploitation one, and I remember I tweeted out and said I have a retired content from 760, the SAN 760 course on exploit development, and would anybody be interested in seeing it, even though it's a bit old? And people said yes. So I did that one. That one seemed to go over pretty well. It's got quite a few views. And I said in that video that I was going to continue talking about browser stuff at some point in the future. Well, it's been some time now, and I figured, oh, it's what time? No time is better than now to bring that back in. So the original one that I did was Internet Explorer 7, and it was a use after free vulnerability discovered in like 2014. It was discovered in the wild, being used actively as a 0-day by FireEye. They're the ones that saw that it was being used in the wild. And dark theme, don't get your hopes up. I'm not using dark theme. There's actually something funny to that. So when you're doing presentations on like projectors, and especially like in the classroom and such, I've surveyed this so many times. It's easier for people, especially with visually impaired individuals. It's easier for them to see not in dark mode, at least in my experience when I've asked that question so many times. Believe me, I do use dark mode on my own stuff, but it's kind of like, AT&T syntax versus Intel. Most people choose Intel, but there's a few people out there that are AT&T folks. So anyway, the first one was the 2014 bug discovered by FireEye being used in the wild. I think that might have been the one that affected the Department of Labor in the United States. So basically with these exploits, these 0 days that were use after free and type confusion bugs in the browser, they were going off back in 2012, 13, 14. And that was before Microsoft implemented those two big protections, MemGC and isolated heap. Once they put those things out there, it really mitigated the majority of those browser vulnerabilities. It was quite an effective mitigation, especially MemGC. And so that was in June and July of 2014. I would say each month on Patch Tuesday, there was anywhere from like 20 to 50 browser memory corruption vulnerabilities being patched, which is insane, right? So it took them long enough, but finally they got a pretty effective mitigation in there, and that really, again, it worked. I remember Skylined, if you're familiar with that individual researcher, Bron Jan Weaver. I can't pronounce his name properly, but he's the one that first disclosed heap spraying as a technique way back in like 2005 or something. I don't know. It was a long time ago. And I remember he tweeted out right after Microsoft implemented those mitigations and said, does anyone have a MemGC bypass? Because basically he was sitting on a handful of use after free vulnerabilities that you now couldn't exploit. So the vulnerability was there, but you couldn't exploit it because that protection was so strong. And I'll talk about that protection a little bit, because in this presentation today, we're dealing, MemGC is on, and so is isolated heap, but we're avoiding it by exploiting a use after free vulnerability that has to do with text allocations. And text allocations were not protected with those mitigations, because those mitigations were focusing on HTML objects or elements like span, div, button, table, all those different HTML objects. And so the text allocations just avoided it altogether. And this particular vulnerability that I'm going to talk about was discovered by Ivan Fratrick from Google Project Zero. He wrote a really nice browser fuzzer that he ended up making open source. I'm not sure in his case, but a lot of people, when they release these fuzzers and such, it's because it ran its course. Like, they did what they needed to do with it, and maybe the low-hanging fruit has been picked, and then they released that. Again, I'm not saying that was the case for him, but a lot of times when you see this different type of tools or research being released, I said this before too, when I had Jeroen Beckers on a few weeks ago, we talked about mobile device hacking, and like, you know, there's a Pegasus group out there, and there's these different groups focused on iOS jailbreak remote 0-day things. It was that one I just tweeted yesterday. It was a tweet from I can't remember, it's Kaspersky or something like that. Anyway, it was a interesting iOS vulnerability that's been out there actively exploiting for like years and years and years, and still works on the latest iOS version, fully patched today. Like, that's pretty terrifying. But that type of research, the people who know how to do that, it's held close to the chest, and they don't share that information. Like what you typically read in publications or blogs and such, that's old information. So like that blog that was released yesterday or the day before, that one has some pretty interesting information, but it's not very detailed, you know, because someone's dealing with an infected phone and they're just using Wireshark to look at the traffic and try to determine what the actions are of this particular exploit. You know, and a lot of times it's these full chain exploits. It's these full chain exploits that, you know, back in the day, like when I did my first browser demonstration or walkthrough back in September, that was a single exploit that allowed for full remote code execution. One single exploit. And the reason that one only needed one, because ASLR was on, because normally you need a memory disclosure or information disclosure vulnerability. But that one, that was the time when Java Runtime Environment 6 was out, and there was an infamous DLL, MSVCR71. I remember it because it was infamous. That DLL did not participate in any mitigations, and it came with Java Runtime Environment. So you just avoided ASLR altogether by using a non-rebased module. This particular one that we're going to look at today is one piece of a two-part chain. So chains can be anywhere from 2 to 4 or more. Like a lot of these iOS ones, there's the initial, there's an information disclosure vulnerability to get around ASLR so that you can use relative offsets from based modules. And then you've got the remote code execution bug. So there's 2, information disclosure and then remote code execution. Then you need a sandbox escape. Then you need a privilege escalation. So 4 are oftentimes what's required to get a full working chain. And a lot of the buyers out there that I've worked with over the years, they don't want just a single piece of a chain anymore. They want a fully weaponized chain. I mean, sometimes they'll buy a single piece if they need it, but they want the whole thing. Now that depends on the buyer too, because if you're talking about a buyer like iDefense or ZDI, Tipping Point, they'll buy just a piece of it because they're going to actually take it to the affected vendor and work on getting it patched. So cool. Just looking at. So that's what is meant by chain. I know most of you on here, you know that. You know what a chain is when we talk about an exploit chain. So iOS 0-day case, what do you think? Intentional by the vendor? Yeah, I don't. That's a tough one because that's the big conspiracy stuff, right? People are like, do vendors like Apple, for example, which you wouldn't think they would because they're very privacy oriented, did they intentionally introduce this vulnerability so that it can be used by government agencies, right? Intelligence to be able to exploit systems used in other countries. I mean, that's conspiracy stuff. I have no idea. I really don't have an opinion on that stuff. I would say anything's possible for sure. But so we've got this chain. This one that we're looking at is a 2-chain exploit. One piece that we're going to look at is the information disclosure memory, the ASLR bypass. And then the other piece is, in this case, is a type confusion vulnerability that allows for remote code execution. So you need both of those things. Both of these vulnerabilities were discovered by Ivan Fratrick, and what Google Project Zero at the time was doing, and they're still pretty much doing the same thing. They say, okay, we're going to inform the affected vendor, and we give them a 60-day notification. You've got 60 days to fix this, or else we're going to release it publicly. And it's kind of automated. So 60 days goes by, boop, it gets posted. And that's what happened with both of these vulnerabilities. And I remember Ivan saying he was actually surprised that Microsoft didn't address it in time and get it fixed. So now you've got a public trigger file that can be weaponized and used as a 0-day at this point because there's no patch available. So what groups like Project Zero in that case typically do is they release what I call a trigger. The trigger triggers the vulnerability, but they don't weaponize it for you. You've got to weaponize it. So a lot of times, like when I've sold exploits in the past, it's just a trigger that I give them. And the person who reviews it, if they know what they're doing, which they should, they can look at the results of the trigger file and they can see that, oh, clearly this allows for an information disclosure or a remote code execution or whatever it is. Because if you know what to look for, you can look at the registers and the call stack and memory, and you can say, okay, this is clearly exploitable, or at least it should be. So that's what I mean by trigger. So Project Zero released 2 triggers. One was in like December and one was in January of whatever year it was. And you could weaponize them. So I remember this happened back when I was working on Gray Hat Hacking 5th edition, I think it was. And I needed a target vulnerability to use in the chapter in the book on advanced Windows exploitation, but I wasn't going to use one that I found, because then I lose that money. I mean, once you find a vulnerability and you sell it to a vendor or to whatever, it's not your bug anymore. But you're not even supposed to talk about it, because then they can come after you and say, hey, you're like trying to sell this thing twice or something. A lot of these exploit buyers, they make you wait 60 days, 90 days, whatever. And the money is held in like a, what do you call it? What's that word I'm looking for? It's held by like a broker or whatever you want to call it. Somebody who's going to hold on to it. And as soon as the terms are met, then they release the funds, right? So that's pretty common, because they want to make sure you're not going to go out there and sell it to a bunch of different people all at once and try to make all the money. So it makes sense. Escrow, thank you. That's exactly what I was looking for, escrow. So that I wasn't going to use one that I found, because then I would lose that money. I can't use one I found, or else I'm giving up $20,000, $50,000. So this was a perfect situation. Ivan Fratrick, right when I needed to write this chapter, that got released on Project Zero blog. And I was like, sweet, this is perfect. Because what it allowed me to do was document the process of weaponizing the vulnerability, because the chapter wasn't about browser fuzzing. It was about weaponizing a vulnerability. Most of these browser vulnerabilities are found through fuzzing. You teach your fuzzer to write all kinds of wacky JavaScript, and hopefully you get a crash. So we'll talk more about that in a moment. But I documented the steps I took to weaponize it, to make it a full information disclosure vulnerability. And that was the point. Okay, so what I want to do here at first is I want to walk through a set of slides to talk about this specific vulnerability and what it's doing. All right, so this trigger, so on the right there, that is the proof of concept code that Ivan Fratrick released. That's all you got. There was nothing more to it. So if you're somebody who knows how to do stack smashing, and you know how to send in a bunch of A's as a command line argument, and then the process crashes and you see in a register 41414141, you clearly know that what you just did had your desired result. Like, you know that you must have overwritten a return pointer or something. With these kind of vulnerabilities, browser vulnerabilities like this, you typically don't see anything meaningful in the registers. So you're just going to see a bunch of random memory addresses. Yeah, I'm actually talking to some people about that. So about fuzzing. So a comment came up saying we're hoping to have a session on fuzzing. I'm talking to some people about that. I used to have a fuzzing farm for browser fuzzing specifically, but when 2014 happened, it just killed it. Like, I mean, I ran it for a while after that, but I think I found like one vulnerability in a year, and that's just it's not worth it. Before that, though, I was finding maybe a dozen per year, like one per month on average. Usually it'd be some, if you've heard me lecture, you probably heard me say this before, but like I owe Ivan Fratrick beers, because like this right here, this trigger file on the screen, I look at that and I say, if that caused a crash to occur, there's probably other similar vulnerabilities within the same area. So I use these trigger files as a seed file to my mutation engine. I'll call it an engine, even though it's like duct taped together, a bunch of C++ code. But it would take this and do variations of it. And a lot of times you would find other crashes in the relative area. And Microsoft historically has sometimes been bad about doing a thorough job looking for the same vulnerability existing in other relative or similar areas. It happens a lot. I can give you many examples. But anyway, my point is these trigger files can sometimes be used as like a seed file to a mutation engine to go and try to find other vulnerabilities in the same area, is my point. So this is a trigger file. What that means is when you open up this JavaScript inside an HTML document in a vulnerable browser version, the browser should crash or it should do something. Now, there's a interesting problem here as well. This is a tricky thing that I had to learn and figure out how I was going to deal with it. Usually, the use after free bugs that I had dealt with originally, they were all remote code execution vulnerabilities. And the reason that was the case is because I didn't know how to look for other types of use after free vulnerabilities. So they were probably happening, but I wasn't catching them because I didn't know what to look for. And it wasn't just obviously crashing the browser. So information disclosure vulnerabilities, again, that's a vulnerability that's allowing you to get around ASLR. And that's pretty much mandatory at this point. So my point is, when you have an information disclosure vulnerability in something like a browser or a word processing application, it's not necessarily going to crash the system, your browser. Your browser may act completely normal, but you actually triggered a bug, but you didn't see it. And you'll see what I mean as we're going through. So there are things you can do to try and make it so you don't miss those, but it requires turning on tools like PageHeap, using with GFlags and stuff in the debugger, and it takes more processor overhead and it takes more work, but it makes it so you don't miss certain things. And then when a crash occurs, you've got to know how to triage it, have like a post-mortem script run to take a look to see if it's something that looks interesting or exploitable. You don't have time to sit there. I mean, I guess you could have time, but it's going to slow you down big time. If you have to go and manually inspect every single crash, because most of the times I've been able to get browsers to crash, it's not actually an exploitable condition. It's a bug that causes the process to crash, but it's nothing exploitable about it. So you don't want to waste your time looking at bugs that aren't exploitable all day long. So writing a little post-mortem script, like you might have heard of Bang Exploitable. That's an old WinDebug extension that has limited functionality and results. But the point is that when you run it, it looks at the registers and it looks at other things, the disassembly and such, and it tries to determine whether or not it's an exploitable condition. And then it's something worth looking at. That's my point. So on the screen, that's the trigger file. That's all that Ivan released, along with this note. And the note says, because text allocations aren't protected by MemGC and happen to be on the process heap, use after free bugs dealing with text allocations are still exploitable at that time. That was awesome news, right? Because this affected IE11 and Edge. And the funny thing is IE11 is a 64-bit parent process, but the actual browser windows are 32-bit. Why? I have no idea, but that made it a bit easier to debug or exploit in some cases. So 64-bit parent process, each browser window, though, through the broker is going to be a 32-bit process. IE11 is the last version of Internet Explorer, and it's still used out there, sadly. And the reason it's still used, even if you don't use it, believe me, it's still used. A lot of companies out there have written applications that work specifically with Internet Explorer. This is why Windows 7 with IE7 was such a pain point, because that was the default browser with Windows 7. IE8, not IE7, IE8. IE8 was the default with Windows 7, and that was used by everybody at the time in like enterprise corporate environments. And so these companies would write applications internally that work with Internet Explorer 8 because Windows 7 was super popular. And then when the newer versions of the browser come out, you're kind of stuck with Internet Explorer. So a lot of companies end up getting stuck because IE11 and Chrome were the two default browsers on Windows 10 when it came out. Then Windows 11, obviously they wanted you to get away from that and go move on to Edge. And then Edge was out for a while, behaving very much like Internet Explorer did, but then they moved over to Chromium. So lots of changes there. Okay, so let's move on. This is the trigger. We're going to walk through this trigger right now and try to understand what it's doing. Okay, so we're going to start at the bottom here. This is a text area element. That's a type of HTML element or object, right? Text area. It's just a little like box where you can put text. Then, so you've got this box there, this rectangular window that is your text area. And inside of it, you can put your inner HTML, I guess we'll call it. In this example, you can see we're putting a bunch of lowercase a's in there. So if you were to view this document in the browser without letting the JavaScript function run, you would just see a text area element with a bunch of a's inside of it. That's it. You can see there is a body on load, execute the run JavaScript function. Okay, so the first thing we talked about in this trigger file is a little text area element that gets created. We've got a form and some a's inside of the text area, and calls equals 80. That's the width of the text area element. And you can change all this stuff, which is actually end up going to be important here soon. So next up, okay, we execute the body onload run function. So the run function is going to execute now. So at the top there, you can see inside the run function, we create a variable called text area. And we use the get element by ID JavaScript function to go and fetch the text area element from the document body. So we go and fetch that and bring it into our JavaScript function. Then right below that, we create a new variable called frame, and we create an iframe element. So now we're using the create element JavaScript function to create an iframe that we're calling frame. Now, JavaScript and HTML, well, especially HTML, is not a real language, right? It's not, you're not a programmer if you write an HTML. It's what this is doing when you say create element iframe, you're telling JavaScript to interact with the underlying C++ libraries to create that object. So C++, there's a class. Every HTML element has an associated C++ class. And there's going to be a create element function within that class, and it's going to be a destructor within that class. We'll get back to that. Below that, you see we're saying text area dot append as a child the iframe. So we're appending to the text area element. So that's going to cause a reference to occur. So there's now going to be a reference because you've got this text area element with a child, which is the iframe right now. Serving this page from web server crashes users. Serving this page from a web server crashes users IE11. Yeah, exactly. That's the point. I think I meant to say that earlier when the last browser vulnerability we looked at, I think that's the one that affected the Department of Labor website. And the idea is an attacker would compromise an organization's website, and they would hide in there, typically in an iframe, the JavaScript that triggers the use after free vulnerability. So, okay, that's all we've done in this function so far. We've created a couple of variables, and we've appended the iframe as a child to the text area element. Next up, we've got this frame.content.document.onReady state change equals event handler. So when a browser is loading its document and parsing through the HTML and all that, it's going through one of a series of ready states. Loading is an example. So when you view the HTML document and everything's done, it's in a specific state. I forget what the state's called, but it's basically it's done. It's been processed. What we're saying here is if the state of the iframe changes, fire off an event handler. And then below that, you see form.reset. That's going to change the ready state of the document, of the iframe, which is going to fire off the event handler function. So pretty simple, right? What's going on right now? This is actually a weird use after free vulnerability, because this is barely any code, and it actually crashes the browser if you're paying attention and or you know what you're looking for. It's weird. Normally there's a lot more JavaScript involved. So anyway, that form.reset is going to change the ready state. Now we're going to fire off the event handler. Now we're down in the event handler. This is code that's going to execute when the ready state changes. So this says, go and get the text area element again from the document body itself, right? So we're grabbing the text area element, but look what we're doing. Dot default value, in other words, inner HTML, equals foo. That means those A's down at the bottom, all those A's that I'm pointing at the very bottom, that's supposed to change from A's to just foo, 3 characters. And then below that, there's a little alert that's not needed to execute the vulnerability at all. That's just what I've been put in there and said, text value freed can be reallocated here, indicating that this is a use after free vulnerability, because he's saying that the text body of A's, all those A's have now been freed, and you should be able to replace that freed memory if you try to create something that's the same or similar size. It should go and use and recycle that memory. Browsers, a lot of applications or memory managers for the longest time was last in, first out to try and be sensitive to overhead. Last in, first out's fast. But that's from a security perspective, not the best option, because it allows for things like grooming the heap to be a lot easier, versus if we're randomly allocating from a doubly linked free list or the low fragmentation heap or whatever, it's going to make it more difficult for an attacker to know what's being returned as a memory address, what chunks being returned. So why would this say text value freed? Because what should happen here is the heap is supposed to be very optimized. The heap, we have rules like no 2 free chunks of memory should be adjacent to one another and be freed at the same time. Like you would coalesce or merge that. You want to reduce fragmentation. We want to optimize, because the heap is so heavily used. We've got 2 primary locations where user-based memory and such are being allocated, right? The stack and the heap. But yeah, there are other areas, but those are the 2 big ones. And the stack is there for function calls. Every function call gets a stack frame, but it's got a finite lifetime. You have a function prologue when you call a function. You have a function epilogue when you return out of the function. No state is preserved. The heap is for dynamic allocations, and that's what we're dealing with here. So the heap, you're going to have thousands and thousands of chunks allocated at any one time. So you've got to make sure things are in order and optimized. Otherwise, you're going to be asking the kernel for more resources than you need, and you're going to be very wasteful. So brings me to my point here. When we're changing the inner HTML to foo from these 20 plus A's, what should happen is we do a heap realloc call. You've probably heard of the realloc function if you know Linux. On Windows, it's heap realloc. It's just a wrapper to the plain old realloc function. There's a few primary functions that we use on the heap that has to do with memory allocations and free. We got malloc or heap alloc on Windows. We've got realloc or heap realloc. We've got free or heap free. And then we typically have calloc, which allows you to specify a number of chunks of the same size, and you get returned back the pointer to the adjacent array in memory that you've requested. So this would result in a call to heap realloc, because what's supposed to happen is you're supposed to allocate memory to hold foo, F-O-O, which is a lot smaller than all those A's. And then you're supposed to go and free the old memory where the A's were, give it back to the heap manager to make it available for reuse. So you see the point? We're just trying to optimize the heap and not be wasteful. So since we're changing the inner HTML to foo, We allocate a small chunk of memory to hold foo, and then we free the old memory. What's supposed to happen there is pointers need to be updated, because if there are references to this object or this allocation, if there are references to those A's, that needs to be updated anywhere there's a reference. If something gets missed and it doesn't get updated, you're going to have a situation where there's a reference to memory that has been freed and probably reallocated by that point. So when you go to access that reference, you're going to be accessing something that's you're not supposed to be accessing. And that's why this results in a memory leak, because you'll see in a moment here in the browser window, you see something you're not supposed to be seeing. You'll see some strange Unicode characters, and that's indicative of a memory leak. At least that's one way, but it's real easy to miss. Somebody says, if this is a trigger using JavaScript, someone who plans to weaponize still use the same JavaScript. Wait, let me read it again. If this is the trigger using JavaScript, someone who plans on weaponizing will still use the same JavaScript to control the memory. I'm not sure I can follow the question there. If you can try changing the wording, it might help me a bit. But yeah, I mean, the attacker would need to take this trigger right here and weaponize it. And that's what I'm going to walk you through. How do you go about weaponizing this? Because sometimes you get real lucky. Other time it's hard. No, I don't stream on Twitch. I just use StreamYard to stream out to Twitter, LinkedIn, and YouTube as a service to my community. So let's go over to the Windows box now. All right, so this is the Windows 7 system with IE11 running. So if you wanted to actually practice this, and what I'll do after this is over, I will upload the trigger file so that you can, well, I'll probably just put the URL up if I can find it to Chromium or Project Zero where it was, because it's still out there. And if you want to repeat this and try it on your own, just go get a default Windows 7 box with IE11. The problem is you need an IE11 version that's like preferably the base version, and you should still be able to find that, because if it's fully patched and updated, this isn't going to work. It's not going to crash the browser, of course. So, okay, we've got the trigger file. Let's open that up first. So the trigger file is right here. So you can see it's exactly what we just saw on the slide. And there's our A's down there at the bottom. Nothing has been changed here at all from that. So what I want to do first is just run the trigger file so you can see what happens. And that will show you what I mean by how you can miss this bug, because this is the trigger that triggers a vulnerability. Watch what happens though. I'm going to run it right now. So trigger, double click it. So this is what Ivan Fradrick put in as that little pop-up. That's why you're seeing that pop-up come up. Text value free can be reallocated. So I say okay, and look what we see. See those two Unicode characters? Those are obviously Asian. I don't know if they're Korean or Chinese or whatever, but those are not supposed to be there. Those are either supposed to be A's or they're supposed to be foo, but not that. But did the browser crash? No, the browser's fine. We can navigate and do everything we need to do. Now, we're lucky in this situation where we can visually see the result. And if you are looking at this, you know something's off. But here's the problem. If you're fuzzing and the fuzzer found this, the fuzzer doesn't know that that's there. So how does the fuzzer catch it? You need to turn on PageHeap. PageHeap's going to, oh, thanks, Sarah. It's Chinese. So by community, I was just joking, meaning the security community. So no, I don't have a Discord either. I'm lazy. I just do this to like help people who want to see some fancy stuff. All right, so if we refresh right now, watch what happens. See how it changes? Now it's like, I don't know what those are, other characters, right? So these are Unicode characters. If we look at the memory address of this, well, actually, in other words, what we need to do is take those values and stick them in a Unicode to hex converter so that we can see what memory address is being leaked. that's how this works. What we're seeing are these strange Unicode characters, but that's not really what they're supposed to be. It's actually a memory address being taken as if it were Unicode characters. So that's the leak. If you go and put this in a converter, the hexadecimal memory addressing that comes up is the address being leaked. So it's pretty neat. Now, again, you can see how you would miss this. So how do you get the fuzzer to catch this then? Well, that's what I was saying before. You got to turn on PageHeap. So watch what happens now. I'm going to close that. I'm going down here and we're going to say GFlags. That's a debugging tool that comes with Visual Studio. GFlags, and then I'll say /P for PageHeap, enable the process we want to enable it on, because you don't want to use PageHeap unless you have to. It's very greedy when it comes to memory. It's a waste of resources. So I'm going to say explore.exe. Make sure you type that right, because I've done it before where I typed explorer.exe, and no, that's the wrong application, or you have a misspelling here. It'll happily just keep going, and it doesn't tell you anything's wrong. And then I'm going to say /full. Now, the reason I say /full is because a funny thing here, if you don't turn on full PageHeap and you just do partial PageHeap, it doesn't catch the bug. Just weird, things you have to deal with sometimes. So now, wait, what did I do here? It says scenario can be used x86 binaries, but not native. No applications PageHeap enabled. What did I do wrong here? This should just work. Oh, I think no, I'm in program files x86. This should be fine. Why is it being difficult? Let's see here. P enable. I have no idea. Look at that. It's the exact same syntax, and this time it said it turned it on. The first time it said it wouldn't. Now, I'll remind you, remember I said that the parent process is 64-bit, but the child process is 32-bit. So this will be fine. This is good. So now I'm going to run the trigger file again. Watch. We run it. Same thing as before. Now look at the result here. No crash happened, but watch what happens when I refresh it. I refresh this, and bam, postmortem debugger kicks in. This is what we need to happen so we don't miss the crash if you've got a fuzzing session running. And obviously we would use a command line version instead of graphical, but like it's easy to miss browser bugs because of this weirdness right here. So what this taught me back then was to make sure that I do a couple extra little things. Like you saw it here where it didn't crash until I refreshed it once, and then it crashed. So back when I had my fuzzing farm running, I would instrument that into it. Like when it would look at a mutation file, it would refresh a couple of times to make sure that there was no crashes being missed. I made sure I had PageHeap full on, all these other things that you learn along the way. Somebody says, why? Yeah, sure, you could add me. Thanks. Why, when you refresh, does the address change for the leak? Or I would think it was static address. No, that's the weirdness of it. So first off, ASLR is the main answer. Like the libraries, when you reboot a Windows system, they rebase, but they don't rebase each time you start the process up. They stay rebased to the same address until you power it down and reboot it again. That's different than on Linux, right? On Linux, the libraries are rebased every single time you run a process, but Windows, they're not. Now, to answer your question more completely, no, it's going to be different a lot of the time. Oh, there's a slash. Okay, thanks. That's what I must have missed. Typo. So remember what's happening here. The memory involved in the use after free is getting freed, and then it's available by any other thing that wants it. So oftentimes it's not always going to be the same thing that ends up using that slot of memory, because when you refresh, all that memory is getting freed and then made available again for reallocation. So it should be the same for the first time you start the process up and do a thing. It should always be the same. But when you do something like refresh, You're freeing the memory. All that memory is available again for reallocation, and it's changing the order of execution and such. So we refresh, we get this crash. Now look at the crash. It says move with 0 extend. We're taking whatever ESI is pointing to, what's stored there, we're dereferencing basically, and loading that into the accumulator register, lower 2 bytes, because move with 0 extend does a lower 2 bytes. And you can see it says over to the right that the address that ESI is pointing to, question marks, because it's not currently in use memory. That's what's causing the crash. So the crash is happening because when this instruction inside WCS copy tries to go and dereference something, that something is not there. There's nothing there. So that's what we're running into. That's why the crash is occurring. Now, that doesn't really answer a lot of the questions as to how we would weaponize this and all that kind of stuff. But what I wanted you to see right here is how easy it is to miss these crashes, and how when you look at the registers right now, you don't see anything meaningful like 41414141 in a register. Like those are all arbitrary addresses that are going to be pointing to things like C++ objects and virtual function tables and whatever else is going on. But this is where we're crashing. Now, in the use after free vulnerabilities that end up with code execution, so this is not a code execution possible use after free. I had told you originally, like when I first started working with use after free vulnerabilities, they were all remote code execution ones because I thought they all were. I didn't know that there were other types of useful things you could get from a use after free vulnerability. I remember I was working with one, and this one use after free vulnerability, it only allowed you to write a single byte to a arbitrary destination address. So basically it was a and you couldn't control it either. It was a, what we want in a perfect world is write, what, where primitives, where we can write anything we want to any address we want. This was a situation where a byte that you couldn't control would be written to an address that you could control. So it ended up being enough. Like you would think that if all you have with a vulnerability that you're trying to weaponize, if all you can get out of it is a single byte overwrite in memory, that wouldn't be very useful. But it ends up being enough in that case. Back in that particular bug I'm talking about, what we did was overwrote the most significant byte of a sprayed region of memory. We did a heap spray using flash objects at that time. There were flash sound objects. You do a heap spray with the sound objects, and we would overwrite, because when you do a heap spray, the reason you're doing it is you're filling up memory so that you get to predictable addressing. You bypass ASLR by filling up memory with a bunch of junk to the point where you've sprayed so much memory, you've exhausted it all pretty much, that you get to predictable addressing. You know that something specific is going to be at a specific address. And we would overwrite the most significant byte at that address, which ends up being the size member of the object. And basically that would allow flash access to all user land memory. And it would be enough to bypass an ASLR and get remote code execution. So that was a case where a single byte of memory could be overwritten via use after free vulnerability. This one is a memory leak use after free vulnerability. And the normal ones I was talking about were remote code execution use after free vulnerability. So there's all different types, and each of them are useful in their own way. So Sarah said, so the root cause of the crash is the program trying to access a memory region not existing. Yeah, there's nothing at that address. It's not mapped. It's not even that it's just freed. It's just not actually been mapped from virtual to physical addressing. So there's no page table entry for it. All right, so that's all I wanted to say here. Now, I was showing you how you could easily miss this, what we're seeing right now, because normally what I would do is this. I would take this function that's involved in the crash, and we'd say unassemble the function, give it that, and we'd look to see, well, where was the line involved in this? This was plus offset 4.6, and we're looking for move ZX EAX. So let me see how big this function is. So here's that line of code right there. This is where the crash occurred. And what I would normally do is look around, especially below this, to see if there was a call to a function. Because like the first webcaster stream that I did on this topic, we saw right after the instruction where the crash was occurring that there was a dereference to an offset in a virtual function table followed by a call to the address in the register. And that was immediate code execution. This one, there's no call down below there. So this, like, I mean, obviously we could look further into it, but there's no code execution opportunity here. What's the impact severity? The impact, I mean, Microsoft would consider this important. I would consider it critical because it allows you to get full ASLR bypass, which is a required component of an exploit chain. So your remote code execution vulnerability is no good if you can't bypass ASLR. So you need both of them. So that's what the impact is here. We can bypass ASLR. All right, so let me close the debugger now. All right, I'm going to turn PageHeap off. We don't want to deal with that. All right, PageHeap disabled. Just making sure it says that right there. Disabled. Okay. Thank you. All right. Now, next up, what do we want to do? Next thing I'm going to show you is how we can go about potentially controlling the characters that are showing up inside the browser window, because that's like there's something that's kind of difficult to explain, but I'll explain it. Someone had asked earlier, like, well, why is the thing changing that's being leaked? Like, wouldn't it always be the same? And I said, well, if it's a fresh process, it should always be the same thing that gets leaked. Now, the more complex the process is, like if you've got a process that's running and that user has been using that browser window all day long to go in Chrome and YouTube and TikTok, there's going to be a lot of messy memory out there. Like the state of the heap, that's why we do heap grooming and stuff in some cases, because the heap can be in a really ugly state. You don't get a nice clean heap. So you've got to kind of put things together in a certain way. What we need to be able to do is make it so it's consistent and it's reliable, so that the same thing always gets leaked. Sometimes you get lucky. Most of the time you don't. What we need to leak is what we want to leak is a address of something inside a DLL that we can find so that we can subtract its relative offset to recover the base address of that DLL. And not just any DLL. We need a DLL that's going to give us enough ROP gadgets to bypass or to allow us to build our ROP chain to call virtual protect or alloc or whatever. So we need to basically massage or groom this vulnerability so that we can control what's being leaked. And that ends up being a very tedious part. That's frustrating. Cool. Thanks. Appreciate it. So I'll explain more to you about this in a moment. Let me go ahead and run a trigger again. And we'll look at something cool here. So look what's been leaked here. Now, look at those characters. Actually, I'm going to take a screenshot, and we'll bring up Microsoft Paint. I'm going to paste that in. So there's our screenshot. I'm going to close this browser, and we're going to run the trigger file again to see if the same characters leak. That didn't. Like, now look at it. It's a square with a bunch of A's. So let's kill it. Run it again. Square with a bunch of A's. So we're not getting the same thing now. Now we got it again. So see that? It matches. But it's inconsistent. It's not every time the same thing. We need to make sure that this is consistent every single time, or else our exploit's only going to work some of the time. And if you're actually dealing with a 0 day, you don't want that to happen because it could crash things. You're more likely to get caught. So you need it to be very stable. Either way, let's pretend that this thing was always the same. I'm going to grab these characters here, these two, Control C. I'm going to go out and we're going to bring up a Unicode converter here. So here's a Unicode converter. I'm going to paste in to here those characters, and say convert. And look what we get. 74CC8AE0. This right here. I'm going to copy that. I'm going to go back in here. And we've got that. So let me just change the font size here. And let's fix this. So put the second half to the first half. That's our address. So this is what's being leaked right now. And that is a memory address. So what we'd want to do is take this memory address and attach to this with the debugger and see what it is. So I'm going to bring up WinDebug, WinBag, whatever you want to call it. When you look here, notice that there's a couple instances of Internet Explorer. I know it's probably small on your screen, but there's a couple instances. Go with the bottom one because there's a broker there, the browser broker that started with IE11, where to make it so if a browser window crashes, it doesn't kill the whole parent process. They started doing that. And also sandboxing and things like that, you're going to see multiple instances of the process. So in this case, with Internet Explorer, we've only got one browser window. It's always going to be the bottom one. So we say, okay, we've now attached. And now I'm going to say DT and give it that address. And look what it says, ctext event sync virtual function table. This actually ends up being extremely cool. Like, this is rare that magically what we're getting is a virtual function table, because this is really easy for us to determine the base address now. Because what we want to do is say, okay, well, this address here, if I take it and we say bang address, actually I'll say list nearest first. Nothing good there. So let's do a bang address. And it says we're in msctf.dll. So that's the DLL that this virtual function table is being leaked from. So the base address of this DLL is right there, 74CC1000. And the address that we're talking about is 74CC8AE0. So 8AE0. So what we do is we take calculator, and in hexadecimal, we paste in the address that's being leaked, and we subtract the base address of 74CC1000. There's our offset. So 7AE0 is the offset that we would always use if we were getting predictable, a consistent, reliable leak, and it was always that same virtual function table. We know that we can do the maths there. We know that we take the address that's been leaked, we subtract this relative offset, no matter what it is, and we recover the base address of the DLL. Even if we reboot this system and that base address changes, it's fine because the relative offset is always the same size. So we subtract it and we'll always be able to get the DLL base address. Now, the requirement we would need now is, are there enough ROP gadgets inside that DLL? MSCTF, I'll tell you, I know it's not. There's not going to be enough in there. And it's unreliable. Like, we saw that it didn't always give us the same characters. This is where it becomes tedious, because I'm going to show you the next step that you would take. So let's kill this. All right, let's get rid of paint. We don't need that. All right, next step. So I'm going to take the vulnerable code here, or the exploit code, whatever, trigger file. Now, right now, how many A's do we have? 25 A's. So there are 25 A's right there. Now, what I'm going to do is add 4 B's on the end. And I'm intentionally putting a different character so I know that that's the characters I added. What I'm hoping happens is that what's being leaked out now changes. But there's a problem here we're going to run into. And let me try to explain this one. This initial text allocation of these A's, now with the B's at the end, that's what's supposed to be freed so that new memory gets allocated to store foo. And then the reference, that memory where the A's are and the B's should be freed and recycled. The bigger the allocation that I make here, because the more data I put into this initial text string, the bigger the memory allocation is going to be, which means the bigger the hole that is left behind that can be filled by something else that needs that space. You see what I'm saying? Like, I don't have a good analogy, but imagine if you had like 3 different size glasses, like a small one, medium one, and a large one. The small one can only hold so much liquid, but the medium one can hold more liquid. So when you actually empty the medium glass out, it can store something that's a different size than the smaller one. And that sounds silly what I'm saying, but it's important because this is what you have to work with. Like, the hole that you're punching, basically, by making it so this memory gets freed, is then available for reuse by different types of things depending on the size it initially was. Make sense? So depending on how big the initial allocation was, determines what can use that memory after it gets freed. So the bigger it was, the bigger the thing that can go in there. So I just put 4 Bs. Let's save this and let's go and fire off the trigger again. Now look, that's way different than what we've gotten before. Let's see if it happens again. I'm going to kill this, run it again. Same thing again. To know that it's consistent, obviously we want to do it like 100 times or so, but I'm not going to do that. We can see it seems pretty consistent that it's these squares on the screen. I'm not sure I mean, obviously that's not going to be useful to us because we're expecting to see something that's going to be different because it should be something that gets converted into an address. This is all the same thing. So it's not going to, obviously that's not going to be a memory address. So I'm going to kill this and we're going to add in 4 more bytes. So I'll put CCCC, save that. And then run it. And now we get something different. I don't know what that is, but we get that thing. Let's see if it happens again. Same thing. Okay, so we're getting some consistency, but it's a strange character here. Let's kill this. And if this little bit that I'm doing right here seems boring or tedious, believe me, you would need to spend hours, if not days, doing what I'm about to show you. So I'm not gonna do that. I'm gonna cut it short, but I just want you to understand the process. Because now I'm gonna go in and add like 16 Ds. So now I made it quite larger. I saved it. And let's see what we get now. We get foo. Well, that's interesting. Why would we get foo, but then we get a bunch of squares after it. So it actually did update and we're pointing to memory that holds that. Like that's confusing. So let's kill this and run it again. Same thing. So we're getting some consistency, but only that first time did we get those interesting characters that ended up being a memory address. So I'm going to go back to my trigger and I'm not even going to count this time. I'm just going to put in a bunch of characters and save that. See if we get anything different. Nope, now we just get more squares. So it doesn't seem like going in that direction is being very helpful. So I'm going to take it back to the original that we had. I'm actually going to subtract 4A. So 1, 2, 3, 4. Let's see what we get here. We get that interesting character. Is that one character? Wow, that's a tough one. If it's like, if it were Japanese, like hiragana or katakana or kanji or something, that's like, that would be a very difficult character right there. So let's kill this, run it again. Same character. No, it's different. One more time. Yeah, it's inconsistent. Okay, so I think I've done enough demonstrating as to what that does. Now here's where it gets a little more complicated. We need, as I said, not only do we need consistency so that it's reliable, we need it to be something useful. Like I want to leak out mshtml.dll or jscript9.dll or ntdll.dll. Those are big DLLs that I know have enough ROP gadgets in them to allow me to bypass, ASLR or bypass DEP, I mean, by calling virtual protect or virtual alloc. So I want a good DLL, a big one. So we need to be able to figure out how we can control what's being leaked so it's something meaningful. This is where it gets a little tricky, because what I did to make that happen is inside the event handler, I experimented with different types of HTML objects and browser features. I used different JavaScript to try to create different things that would then fill the hole punched by this use after free vulnerability. So remember what's happening. It is going to call heap realloc. It's going to free the old memory where the A's are. It's going to allocate new memory to hold foo. That old memory where the A's were, the size of that memory, how big it was, again, determines what can fit. So these different HTML features and elements that I'm going to be creating, they're not going to work, or they're not going to fill that hole if the hole isn't big enough. That is the massaging that you have to do. That is the irritating part, because you have to make sure that the hole you're punching is the same size as the thing you want to fill the hole after the use after free vulnerability is triggered. They are directly related, and it is boring and time consuming to do that. So I will show you what I used. This here is a script called trigger3. Look what I put here. Now that's the same event handler function that we've been talking about, but I've created a variable called x, and I'm creating an input element, and then I'm setting some basic attributes with really not putting much in them. X.set attribute, type, and range. Now, here's another tricky part. When you create an HTML element like input, for example, that's going to go into an isolated heap. That's a mitigation that Microsoft added back years ago. So all these HTML objects or elements are going to get put into isolation, and that's a problem because we can't access that memory unless we create another element. It used to be the case where with use after free, we would get the memory freed, which would typically be an HTML element, and then we would replace it by creating a JavaScript string. We would just create a basic JavaScript string, and it would of a specific size, and it would fill the hole left behind by the use after free vulnerability. Super simple. But now that doesn't work because all the HTML elements go in the isolated heap, as where JavaScript strings and B strings are going to go into the default process heap. So it's not going to help me anymore. Well, what's good here is, yes, the input element is going to go into the isolated heap, but the attributes like type and range, those are going to go in the process heap. And that's going to be what allows me to fill the hole. Now, remember what I want to do. The memory allocation that happens, I want to try and make it so that it's a C++ object preferably, and that what we leak out is a V pointer, because those end up being really easy to statically find the offset inside the DLL. Doesn't have to be, but it makes it easier. Look down here as well. Remember I said there's a correlation between the size? This number of A's right there, if I were to change that to 25 A's like the original trigger, it would break this, because the hole that's left behind wouldn't be big enough for this to fit in it. Not the literal string there, but the object that's being created. So remember that. I know I've been stressing that quite a bit, but it's important that the hole that you punch with the initial string determines what can fit inside of it when you want to exploit the use after free. So this was a lot of trial and error. I spent hours and hours doing this. Probably longer, probably a day or two doing this. So what we end up getting out of this is a consistent leak. So let me run trigger 3 to show you. So here's trigger 3. We run it. And look what leaks here. This right there. Now, it's the same thing 3 times in a row, and that's fine. It's the same address being leaked 3 times in a row. So if I kill this, though, and run it again, trigger 3, same thing again. See that? And if you run this 100 times, it will always be the same thing. There it is again. And so we do the same thing as before. We grab that. We go into the Unicode converter. We say convert. Here's the address. Copy this. Go over to Notepad and fix it up. 75C6. Then we grab this address, attach to it with the debugger. And we say DT that. And it says C security manager virtual function table. So bang address. It is urlmon.dll. Now urlmon.dll ends up being a big enough DLL that it has all the ROP gadgets we need to be able to exploit or to be able to generate the ROP chain to be able to disable data execution prevention. So I'm going to close this. Now, let me show you something else. So when we talk about the actual exploit, what I did here is created this little JavaScript script that right there you can see the leaked address. It's the same one. That's the address inside of urlmon.dll. And when you click on get leaked address, it actually shows you the address, the base address of the DLL and what it is. So I originally wrote this script when I was selling an exploit to a buyer, and I gave them basically the trigger. And if they knew what they were looking at, they would see it and say, oh, okay, clearly it's an exploitable vulnerability. And but they didn't. They came back to me and said, this doesn't tell us anything. Like, what is this? So I wrote this little script here that basically shows them that we can get the base address and then we can get the actual virtual function table and the DLL. And that still wasn't good enough for them. So I ended up writing a second script, which is this one. It does the first thing, and then it has get ROP chain, and then it gives you your whole ROP chain. So it shows you that by using the leaked DLL that we can populate all the relative offsets to complete the ROP chain. So that's what you would, I mean, that right there. So what you just saw would be the one piece of the chained exploit that would allow you to bypass ASLR and disable data execution prevention. You would combine that then with another vulnerability that would be your remote code execution bug. So the full exploit is this one right here. So if we run it, we should get a calculator on the screen. And there's a calculator. So why that worked is because it took the exploit I just walked you a bit through and it combined it with a remote code execution vulnerability. And that would be a full chain exploit. So let me kill this. And the last thing I'll show real quickly is let's do a little bit of debugging. This is going to be kind of ugly, potentially, in a way. So let me bring this up. I'm going to set a bunch of breakpoints. Now, these breakpoints right here, they are like, the hard part is knowing that these are the breakpoints that you want to set. And the way you're able to find that these are the breakpoints you want to set is by going through the painful debugging process. So I'll explain to you a little bit about what the breakpoints are here in a moment. What I'm going to do, though, is bring up trigger 3. And notice it says, before the creation of text object, attach and set breakpoints. So I intentionally did that so that I can attach to the browser right now, set the breakpoints, and I can walk through a bit of this. So I bring up the debugger here. We'll say attach to process in an Explorer. And now I'm going to paste in those breakpoints all at once. It's going to take it a moment to process it. Let me explain to you a bit about these. So the first one is the create element one. The create element is going to be a function that exists in every class that creates an object, and every HTML object or element has a static size associated with it. So we are setting a breakpoint on the create element function so that we can get the address of the object that's being created. And that will be the object of the A's, of the text area element. So that's why specifically you can see we're setting the breakpoint on C text area create element, because that will be the A's, right? Makes sense. The next one down is set string property. That's kind of like we saw that if you paid attention when I had PageHeap on, when the crash occurred, in the call stack was this basic prop param set string property function. And you'll see why it's useful coming up. It's basically going to lead to a call to heap realloc a little bit later on. And then the insert range, that's basically just doing a bit of inner HTML, like the actual copying part. Like it's very complex in the browser, and you will see enormous call stacks, and you will see your data copied all over the place. So tracking the objects and knowing that the memory address that you're looking at in a debugger corresponds to the exact thing in the browser window is difficult to do. So tracking these allocations and such all over the place can be just tedious. Again, we're going to set a breakpoint on heap realloc. C string allocation, I'm setting one there because I want you to see that this specific allocation happens on the process heap instead of the isolated heap, which of course is getting us around the mitigations that we don't want to have to deal with. And then the other breakpoints, the create security manager and code task memalloc, those are associated with the input object that I'm creating. So we're not going to walk through everything, but let me go ahead and disable these breakpoints. I'm going to enable 0 and 1 specifically, and then we'll say go. Now I'm going to accept the message here. Now you can see we hit the first breakpoint on C text area element create element. So let's look at this specifically. So I'm going to grab that, and we're going to say unassemble the function, paste that in, and if we go up inside the function, once it gets done here, if we go up here, right there, see how the allocation is going inside the isolated heap? That would be a problem. If this was a use after free vulnerability and the object involved in the use after free was freeing on the isolated heap, it makes things more challenging. Not impossible, just more challenging. Actually, that's probably another webcast that I'll do, or stream that I'll do, is showing you example of like a isolated heap bypass. But that's that one. But watch in a little bit, when we're talking about the strings, the text, it's not in the isolated heap. Instead, it's in the process heap. All right, so right now we have hit the breakpoint on create element. I'm going to say breakpoint enable 2, and we're going to say go, go. Now I'm at the breakpoint on C text pointer insert range, and I'm single stepping until we get to this memcopy function. So see the memcopy secure function being called? The address inside EAX, this is the address of the literal text area element on the screen where you'll see the A's. And I'll prove this to you in a second here. So if we say DC on that address, nothing's there right now, but I'm going to say go out. Now when I go out, look what's there now. It's our A's in Unicode. So there are our A's as we wanted to see. So now we know we're hopefully looking at the actual address of the text area in the browser window. So pretty neat. All right, so now that I've done that, let's go ahead. I enabled breakpoint 2. We went out. Let me disable breakpoint 2 and enable breakpoint 3, and we're going to go. Now look where we are now, C string alloc. This is the important thing I want to show you about. Remember, we just looked at the isolated heap. Look at this one. For C string allocations, unassemble function, that guy. Come on. And if we move up, right there, process heap, not isolated heap. So that's what Ivan Fratrick meant by we don't have to worry about it. So it makes our life a lot easier. So cool. Now, next thing I want to see here is the address, and I meant to grab it before. Let me go up here and grab it. This one. DC, that address. Now you can see that our A's are copied there now as well. Where they were originally copied, if I scroll up, right here, this is the original address where they were copied, right? So if I say DC on that address, you can see our A's are there, but they're also here. So why are they in two places? It's very common for your stuff to be in multiple places. One example, like when you send your data in via standard in to a little binary that wants you to enter in a command line argument, and it's copying that data into like a buffer on the stack. Well, it's copying it from some source memory address into a destination buffer. So it's very common for your data to be in multiple places. And again, browsers are extremely complex. So debugging them can be a bit of a learning curve, or a lot of a learning curve. All right, so I'm now going to set a breakpoint. Let me think about this. Breakpoint list. And what do I want to do here? I'm going to enable breakpoint 5. Disable 3, enable 5. Breakpoint 5 is the heap realloc call. I hope I already didn't miss it, but let's go. All right, we broke on heap realloc now. So why I set a breakpoint here is because remember what we're doing in that event handler function. We are changing the inner HTML from A's to foo. So heap realloc is being called because we're doing that. It should be allocating new memory to store foo, and then it should go and free the old memory. So I'm going to hold down F11. It's going to be miserable for a moment. We'll go into the depths of the low fragmentation heap because I want to get to the Memmove function. I would just set a breakpoint on Memmove, but then it sets a breakpoint on memcopy automatically, and that's a nightmare. All right, there we are. We're on Memmove now. So Memmove is the real function that's doing the work. Heap realloc is just a wrapper, right? Then we go to Memmove, which then makes it moves the memory unless it involves the kernel. Then it's going to go into a system call, all that. But the source address and destination address is interesting because we want to be copying foo from somewhere to a destination. So in theory, this destination address is where foo would be stored, but it's not always that easy. And then this this ESI address, right now it's going to be in use. So if we say bang heap minus P minus A, you can see it's busy right now. And I've got EDI's address as well. And if I say go out, look at it again. It's still busy, go out. And now it's free. So that memory that was the source, which should have been probably where the A's were. No, this would be where the foo was initially stored. So, but that's freed now. It's no longer needed. I don't know if it's going to be there, but if we look at the destination address, it's not there. But I was hoping to see foo there. Sometimes it's there, sometimes it's not. Again, it depends on so many different factors. But we would keep going with this, and what you sometimes eventually will see that the addresses that we've been inspecting and looking at will be the ones where the memory leak will be stored. Like, for example, if I say breakpoint disable everything, and then if we go back and we get that the original address, where the A's were, give me a moment. I'm going to assume that what I'm about to come up on here is the original location of the A's. Wow, it's a lot of stuff. There we go. I'm going to grab this address here just in case it matters. Right now, if you look at that address, it's still got the A's. So I'm going to breakpoint disable everything, but we're going to set a new breakpoint, break access breakpoint, read write on that address. And then we're going to say go. All right, so now it's running. It's hanging a little bit because we've been debugging it. It's probably trying to catch up or something. I don't know. Give it a moment here. See if we get access back to our browser window. Oh, I think it's angry at us. Oh, okay. We hit a breakpoint. Breakpoint 7. That's because we did a breakpoint on that object. So if we say DC on that guy now, it's still got the A's. So we say go, breakpoint again, go. But look what's happening now. Something's changing here. Something's getting overwritten. So I'm going to say go again. So we hit. So now the leak is up there. It says replace text with B's. Let me force a break now. And let's look at some of these addresses we've been looking at. Oh, look at that. That's our leak. 75C64504. So we got lucky. And that very first text allocation that we were looking at now holds the leaked address, which is that Unicode that we see in the browser window. So pretty neat. Let me see if I can validate that, because right now, if that's what's there, right, the leaked address is what's there. If we say go, and then I go and replace text with B's, look at that. We hit a breakpoint on that address because it's probably trying to write the B's there now. So if I say go, and now we break, yep, look at that. The B's overrode it. So perfect. It worked out. Like we saw that the very first object that we saw get allocated and saw the A's there is now the object involved in where the memory leak occurred. And then we were able to even replace it with B's and stuff. So it is more challenging than I just made it look to figure that stuff out to get on the specific objects. Some of the times it's not always working that perfectly. But I'm glad it did in this example. I think that's a good place to stop. It's a lot of information right there. Hopefully it was useful for you. I haven't looked at the window in a little while. Way too advanced for me. I've been watching channel. Cool. Appreciate it. Cool. Sweet. Thanks. Video about fuzzing farm. Possibly. I do want to get someone on about fuzzing. It might not be me. It might be me and somebody else, but I'm happy to talk about it as well. Yeah, it'll be on YouTube. This will definitely be on there permanently, so you can go back and watch it, because I know it's a lot of info again. Share my social. I'll just put it in the comment here. It's at that right there is my Twitter handle. What's my current day area of focus regarding exploit dev? Like, what am I currently looking at mostly? I usually pick interesting things in the Windows operating system that I think are meaningful and worth money. For example, that queue jumper vulnerability that came out, that's an interesting one. So stuff like that, stuff like services that are running by default, like DCOM type stuff, MSR, PC, DNS. Recently, I've been looking at terminal services like RDP. So stuff like that, anything that's a big application, that's going to be a pretty critical finding if you look for something. And I did a webcast not too long ago where we looked a bit at like memcopy being the culprit a lot of times, because the size calculation for memcopy is quite complex in some cases. That's like specifically why I looked at MSTSC, Microsoft Terminal Services, is because the compression and the encoding and the encryption, when it comes to memcopy, the size calculations can be miserable and it's quite complex. So I've actually been using ChatGPT to try and help out with a pseudocode sometimes to determine like how that size is being determined, and it's actually been quite useful in some cases. Could we dive a bit more into the exploit dev? That's what we just did. What do you mean? Like, what additional part do you mean? Because I'm happy to talk about different topics and stuff. My Twitter handle isn't returning anything? STEP. Oh, it's the second one. I'm sorry. It's this one. STEPH3N. I think that must be it then, what I just put up there. When I was trying to sell Trigger 3 and they kept asking more and more, were you hesitant to provide it because it was something new? Oh, no, I wasn't worried about that. We already had a a broker set up or an escrow set up for it. That's another thing. I think I talked about it a little bit before when I had like Pedram Amini on, but being careful about selling exploits and the do's and don'ts of that is important, because it's easy to give away something that you shouldn't have given away, and then they're not going to pay you for it. So that's something some people have asked for as well, which I'm happy to talk about. Cool. Yeah. All right. I got to go. I got a meeting coming up in about 5 minutes, but hopefully that was helpful. I had fun with it. It's a neat topic area to talk about, and we will see you next time. Have a great weekend.